This is the FP2 Further Pure Maths 2 Sample paper from Pearson Edexcel. Let's go right into it. Euclidean algorithm is just this minus a bunch of copies of that until you get some remainder that's less than this, so you can just do all this in a calculator, right? I think of it as this minus 3 copies of that to make this remainder, but it's up to you how to do it. Then you use this number and this number next, and there's only one copy that can fit in before you have something too small. And then the next again, you use this number and this number, minus 2 copies, make 35 left over. You can see where this is going now, 42 and 35, this is going to be 1, 7 left over, but of course 35 is 5 lots of 7s, with the 0 left over, and so the highest common factor is 7. Good. The digits can be used in security code of this. Initially, the code is 2 distinct odd digits. Now there are 1, 2, 3, 4, 5 odd digits. I initially didn't even see this and 9 thing there and got the question wrong, but there are 5 odd digits. I just did it by saying, okay, we'll do 5 choose 2, and then you can just arrange those 2 that you've chosen in 2 different ways. So that's how many ways you can do that bit, and then followed by 3 distinct evens. There are 1, 2, 3, 4 evens. Again, you can just pick 3 of those 4, so 4 choose 3, and then there are 3 factorial ways to arrange those once you've done it. If you type that in, you get this. The other way you could have done that is this. You can say there's 5 choices for the first digit because it must be odd and there are 5 of them, 5 odds. There are 4 choices for the second digit because you've already used one of the odds. There are 4 choices for the third digit because it must be even, remember, and you've got 4 evens, then you've got 3 evens left, then 2 evens left, and that also gives you 480. This next bit is very much the same thing. To enable more codes, new system, 2 distinct evens, so you can do it my way if you want to, 4 choose 2, and then times 2 factorial, because there are 2 ways to arrange those 2 evens, followed by any 3 other distinct. So distinct means it still has to be different, so you can't pick any of the 2 you just did. So there are only 7 digits left, and you have to pick 3 of them. And there are 3 factorial ways to arrange those once you've done that. Type that in, you get this. Or of course you could just do this, where you say there are 4 evens to choose them first, then 3, then 7 digits, then 6, then 5, and you get the same number. And then you just take away these 2 answers and you get this here. So a very, very nice, easy first question to get warmed up with. Line with equation this. Now this isn't really a proper equation. We'll call this, if z is x plus I y, you know that the y is 1, the imaginary part, the imaginary coefficient you can think of this as is just 1. So this is going to be z is x plus I. Then of course we can square that to find w, which I can rearrange to be just real part, just imaginary part, if I want to there, and then show that this is a parabola. Well, if w is like u plus vi or something, then you can set the u to be the real part and the v to be the imaginary part, so you get these 2 things. And then you just want to arrange these so that you get an equation for u in terms of v, or for v in terms of u. It doesn't really matter how you do it. So what I did was I just squared this, and then I divided by 4, and then I took away 1, and that gave me u, and I got this. And this, of course, is a parabola. Now just be careful. U is the real part, right? So when I draw this, u is along this axis, and v is along this one. So this is actually a parabola, but not in the usual way up, right? Because this is almost, if you think about it in terms of the more normal letters, this is almost like x equals a quarter y squared minus 1. Right? So it's actually a parabola on its side with a turning point of minus 1 down there. Likewise, you could have rearranged this for the other way around. So you could have, what would you even have to do here, I guess? If you add 1 to both sides here to get u plus 1 is x squared, and then I guess divide. You could square this as well, and then divide that by, and then times that by 4, and you get 4 into u plus 1 is v squared. Would be the other way to write that, which I'm sure is, that's actually just what this is, isn't it? And of course, v squared is like y squared equals a linear function in x is a parabola like this. You see that in FP1, I guess, which you must have had to do to do this paper anyway. So, but yeah, I just do it this way, and then just realize that the graph is the other way around because you've got the x here and the y here in some ways. But anyway, good. Question number 3 is about eigenvalues and eigenvectors. I'll say my usual bit where you need to watch the Blue One Brown's video on eigenvectors and eigenvalues, because otherwise, what are you doing? Of course, m minus lambda I equals 0, the determinant of this thing, I should say. So just take away lambdas from all these, and then do the determinant of that. It's the same thing every single time. This times this times this minus this times this. And then you've got this times this times this minus this times this, and then this times this times this minus this times this. The zeros help you out a lot. It makes this actually a little bit easier. You can pause it if you want to and just make sure all my working is correct, but I'm pretty sure it is. You eventually get this cubic. To show that 4 is an eigenvalue, just use factor theorem, right? Just shove 4 in and you get to 0, so by factor theorem, 4 is an answer to this, which makes it an eigenvalue because it's satisfying this. And then, of course, to find the other ones, well, you could do polynomial division, with lambda minus 4 and this cubic. I never do polynomial division. I just think it's easier to just look at it and see what the answer is going to be. You know there's not going to be in a remainder, so it's fine to do this. Like lambda times lambda squared is well, you need a 1 here to make this single lambda cubed. You need a plus 3 here to make a minus 12. And if you just call this a for a second, you've got 19 lambdas over here. You've got minus 4a lambdas and plus 3 lambdas over there. And you solve this and you get a as minus 4, and you just put that into there. And you can factorize this because it's just a quadratic again. You get this, and you get eigenvalues of 4, 3, and 1. So that's good. Find the corresponding eigenvectors. So we just need to satisfy this equation. So we'll do m times some v, which we'll call x, y, z. We'll start with 4. So let's just do this times this plus this times this plus this times this equals 4x. And then the next one is this times this and this and this and this and this equals 4y, and so on. This actually ends up being very trivial because, of course, when you take away 4z from both sides here, you get x is nothing, which then leads, if you're looking at here, to be y is nothing, or looking here as well, because this and this are pretty similar. And yeah, then of course you just look at this and go, well, z can be literally anything, so we'll just make it 1. And we'll have our first eigenvector of 0, 0, 1. And I'm just saying 4 gives me that eigenvector. This isn't standard notation, but I'm just being lazy. Okay, the next one is using the same thing with 3, so we just do exactly the same thing. This ends up being a little bit less trivial. We can take away 3x here, take away 3y here, and take away 3z here. And we'll actually get the same two equations the first 2 times, and we'll get this the last time. So we can just choose x to be 1, and we can choose y to be 1, and that'll give us z as 1, and that's going to be fine. And that will work quite well. So we'll have this eigenvector next. Then lastly, we'll do it with 1. Exactly the same thing once again. You can simplify these up a little bit by taking away x from both sides, taking away y from both sides, you get the same equations again. And taking away z from both sides, you get something slightly different. Just choose x to be 1, which makes y minus 1, and then you can, and then z would be a third. But actually, if you then, just because I couldn't be bothered to type in a third here, if you make x 3 and y minus 3, then z will be 1, and that gives you a slightly easier vector to write in PowerPoint. And then, of course, for this bit p, you just put this vector next to this vector next to this vector in a matrix like so. And we'll have the entire question. Good. Question number 4 is about group theory. So first we need to do this thing here. So you've got a group. Now, when you read this, first of all, you're thinking, okay, the fact they're calling us group implies certain conditions that it has to meet. So that's important. You have A, B, and E, where E is the identity, so it's got an identity, which is good, because it's a group that must have that. Given this equals this, prove this. Now, this is going to be a proof by contradiction, so let's just assume that AB does equal BA. Now, you're told BA is A squared B, and now, so you can just put that there. Now, because this is a group, that means every element must have an inverse. There must be something you can multiply by it to make E the identity. So I don't know what that inverse is for A, but if I multiply both sides here at the front by whatever A inverse is, then I know these two things will go away and just leave E. And I can do that on the left hand multiply both of these. And of course that gives me just E here and just a single A there, so I get this. But now I can do the same thing with B, but just multiply at the end. So put a B minus 1 here and a B minus 1 there. Whatever the inverse of B is in this group, I don't know what it is, but whatever it is. And of course this cancels for E by definition, and so does this, and you get E as A, but these are distinct elements. So this is a contradiction, right? A needs to be different to E. And so this is a contradiction, and this can't be true. Our initial assumption can't be true. Good. So H then is this group here. So under operation mod 15, so find the order. So the order of an element in a group is essentially the minimum number of times you can multiply or apply the element to itself before getting back to the identity. So it's usually written like this. I see. Yeah, I think I meant to change that. I wrote it in there just to be sarcastic, and I think I meant to change it, but wasn't. You want the smallest k you can find, where when you apply a that many times to itself, you get back to the identity in the group. So for example, 2 applied by itself 2 times 2 is 4, which is just 4 mod 15, and then 2 times 2 times 2 is 8 mod 15. 2 times 2 times 2 times 2 is 16, which is 1 mod 15. So 2 to the 4 is 1 mod 15, so the order of 2 is 4. You have to apply it to itself 4 times to get to the identity. So 2 is order 4. Do the same thing with 4, except 4 is very easy. 4 squared is 16, which is 1 mod 15. So the order of 4 is 2. Next comes 7. It gets a bit harder here because the numbers are a bit larger, but you've got a calculator, right? So it's not that hard. I mean, you need a 1, right? Or a 6 to have any chance of being remainder 1 mod 15. So you just keep going until you find it and then divide by 15 and just see if the calculator gives you remainder 1. That's the laziest possible way of doing it. You get it eventually. So we just do this with all these, and it doesn't take too long. We find a bunch that are order 2 and a bunch that are order 4, and that's all she wrote. 14 actually is a nice one because you can think of 14 as minus 1 mod 15, and of course when you square that you get 1. So 14 must be order 2 without any calculation. Okay, so find 3 subgroups after we've done that. So we've done the order bit. Find 3 subgroups, order 4. Now, subgroups must obey all the rules that regular groups follow, so subgroups must be closed, they must have an identity, must have an inverse, and they must be associative. Now, we're just talking about multiplication here, so we can assume associativity. We don't need to worry about this. Identity means that I just need to have 1 in all of my groups, so basically I have 3 other numbers to choose from. Inverse means that for every number that's in the group, it needs to have another number that will make it 1, the identity, in there. So let's just group some of these numbers up by their inverses then. So 2 and 8 are inverses because 2 times 8 is 16, which is 1 mod 15. So basically what I'm saying here is, if you want to make a subgroup that has 2 in it, it must have 8 in it, and vice versa, right? Because they're each other's inverses. However, if you do that, of course, you've got to have 1. From here, you've got to have 1. You can pick 2 and 8, and then you can pick 14, because as we said, 14 squared is 1, so it's its own inverse, right? 14 times 14 is 1 mod 15, so it's an own inverse. So I can use that fine. The problem with this is that this isn't actually a subgroup, because if you apply 2 to itself, you get 4, and that breaks this rule. The subgroup must be closed. And this is not a closed subgroup, so that doesn't work. And likewise, if you try and say, well, 7 and 13 inverses also, because they multiply to make 91, which is 1 mod 15, you can't make a group like this either, because 7 squared is 49, which is 4, and so it's not closed either. It's interesting that we got 4 both times, and that will be relevant. But okay, so we have to sit here a little bit harder and think, okay, where are these 3 subgroups then? We can't seem to use these very easily. We must be using 1, remember. Well, actually, if you think about 2 squares to 4, which then, if you apply 2 again, you get to 8. And if you apply 2 again, you get to 16, which is 1. So actually, I think that forms a nice little subgroup of 1, 2, 4, 8. Just cycling through 1 times 2, you get back to 1. It's a nice cyclic group. And actually, there's another one of those, which is 1, 7, 13. 1, 7, 4, 13. Right? As I said, 7 squared is 49, which is 4. And then if you apply another 7, you get to 28, which is 13 mod 15. And then if you apply it again, times by 7 again, you get 91, which is back to 1 again. So these are 2 nice cyclic closed groups. Now, where did this one come from? Well, I noticed actually, you can just use all of the ones that have order 2, along with 1. So 4, 11, and 14. Because if they have order 2, that means that they're their own inverses. So this is its own inverse, this is its own inverse, this is its own inverse. So this is going to be closed, right? Well, actually, we should check that it's closed. 4 times 11 is 44. Which is 14 mod 15. 4 times 14 is something that I'm sure is 11, because I have checked mod 15, and 11 times 14 likewise gives you 4 mod 15. I think that's the hardest one to spot. It says describe these subgroups, so you just have to say these 2 groups are cyclic, and you say this group is the Klein group, or just say each element is order 2, something like that, I guess. It's only 1 mark, so don't worry about it too much. Fine, so the last bit then, this is the set we've been talking about. This is a new group here, with all these matrices where k runs from different numbers here. Now, as soon as I saw this group here, this matrix here, I initially thought of this, which is in the formula booklet, anti-clockwise rotation. Now, it's not quite right, is it? It's not quite right, because this minus is in the wrong place. But actually, just putting the minus here, and you can check this through some trial and error, but just putting the minus here just makes it clockwise rotation. And you can just pick some random points and try it out, but it does make just clockwise rotation if you put the minus there. And that's really cool, because if this is clockwise rotation, that means when you apply k as 1, or when you use the element k as 1, that's clockwise rotation pi over 4. When you use k as 2, that's clockwise rotation pi over 2. 3 is clockwise rotation 3 pi over 4. And can you see, this is just going to be a cyclic group, right? Because it's just rotating round. That's why these groups are called cyclic. If you apply k as 1, a bunch of times, you'll get all of these other rotations, right? And of course, this is the identity here, 2 pi over 4 is just 2 pi, so it goes around in a circle. But this is a cyclic group because it's literally going to cycle the whole thing around in a rotation. So okay, this is a cyclic group, J, but this is not a cyclic group. And we know that because there was no element order 7. Right? A cyclic thing means that you take one element and you apply it to itself a bunch of times, and you get through all of the other ones before getting to the identity. But we didn't have this for this. This was, a bunch of them were order 2, some of them were order 4. So this is not cyclic, but this is. So these cannot be isomorphic because they're one cyclic and one isn't, and that's not allowed, right? The isomorphic groups are basically just the same, just written differently. So yeah, those are not cyclic, those are not isomorphics, and that's what we have to say there. Good, so question 5 then is about some integration skills. So we've got the length of the curve, so we look in the formula book. This is a Cartesian curve, so we're going to be using this formula here. So we need dy by dx, so we'll find that first. Of course that's a constant, so it goes away. Cosh derives straight to sinh. The 2 comes out the front to cancel. Square that to get this. And yeah, if you're doing the length of this whole thing, we can see it's clearly symmetrical. So instead of just integrating all the way along, I could just integrate from log a to 0 and then double it. So that's what I'm going to do. I think it would just be easier for me to do that. Of course, we've got 1 plus dy by dx squared in here. But from the formula book again, you get this, which means cosh squared is 1 plus sinh squared, which means this is just cosh squared, and then you can square and root cancel out, sort of, and you just get cosh, which is cool. Integral of cosh is sinh, with a half in it because of this 2 here. And then we can apply these 2 things in here. Now we need to know the definition of sinh to really do this. It's going to be e to the x minus e to the minus x, all divided by 2. So that's the kind of definition. But of course we've got 2x in here, so there are going to be 2 x's in there. And then we can just put in the log a. And of course when you put in the log a, you can start getting some cancelling, which is good. Except you can only cancel once the 2 is up here following power law. And this minus 2 has to move together. You can't move the 2 here on its own and just put a minus there. Well, you can do, but you then can't cancel the in the log immediately. So put the minus 2 up there, and then we can cancel this and cancel this to get a squared minus a to the minus 2. And of course this can be rewritten, I've cancelled this out as well. This can be rewritten as a half into a squared minus 1 over a squared, and so k is a half. Good, and we'll have our answer. So now we're looking at the length of the cross-section. It's required to be 2 meters. So this whole length, which I've just described as this, is required to be equal to 2. So okay, we just set this equal to 2 and we'll solve for a. It's actually just a quadratic hidden, right? You can complete the square if you want to. I don't really care. Whatever you wanted to do here is fine, I guess. You get this. Of course, I've written, I say of course, why haven't I written, oh sorry, I didn't write plus minus here because of this condition. And this minus here, clearly not going to work because you're going to have to square root it. So it's going to be a plus here. Root 5 is bigger than 2, so that wouldn't work. And it's going to be a plus here because of this here. So that's fine. I've got a now. And the reason a was helpful is because I can put that back into, where can I put that back into? If I put it back into here, is apparently what I've done. Yes, because you know this coordinate here is when y is 0 and x is log a. So you substitute in log a into here, and you say y is 0, and I can solve this for a now, because everything else is just known values. Of course, this 2 can move up to the top here to square out that square root, which is really nice of it, and then you can use the definition of cosh, which is e to the x plus e to the minus x, all divided by 2. So we'll use that. Of course, this is acting as our x, which is great because then the e's and the logs, this minus 1 has to move up there first, remember, and then the e's and the logs can cancel. And you get this, and you can type that into a calculator, and you get this. I realized afterwards, actually, you can just type cosh and sinh into calculators, can't you? But it's nice to know how to do this on your own. But you can just type that into a calculator. You get a as this. Now that's not just the y. You're looking for the height of the arch. A isn't just this thing here, because of course when x is 0, substitute x is 0 into here. Cosh of 0 is 1. So actually your y coordinate here is going to be a minus a half times 1, or a minus a half. And a was this, so we take away a half and we get this to 2 significant figures. Find the width of the base. Well, that's just super easy, right? It's just log a plus log a, where a is that value that we found earlier, the root of this, yeah? So it's just 2 lots of that log, which is this. Good. Give the equation of another curve that could be suitable, where the only conditions they want is that we have the same height, or approximately the same height apparently, and the same width. So I'm going to model it with a parabola, and I'm going to say that parabola has to have y-intercept of this, and it has to have roots at 0.7 on either side, 0.7 and minus 0.7. That's where the approximately comes in, because I'm just rounding these numbers off. Now that parabola could look a bit like this. This is a parabola that's upside down because of this minus x, with roots at 0.7 and minus 0.7. However, it's not the right height, right? Because when you multiply that out, you get 0.49. So what I'll do is I'll slam that down by value of 0.49, because now when you multiply this out, you're going to get 0.49 divided by 0.49 is height 1. So I've actually raised it up, haven't I? Because I'm dividing by something less than 1. But then I'll times by 0.62, and I think I'll get something with the right y-intercept and the correct roots as well. So I think that'll do for a curve. Good. Question number 6 then is another complex numbers question. They seem to like to put 2 questions like this in each paper, which is really good because they're really easy, and it's the same thing every time. So just make sure you learn your complex number stuff. Z is of course x plus iy, so you just shove that into there. You group these by real and imaginary parts. You then say that the modulus is defined to be this. If you square both sides, you get this. And so if we square both of these sides, square the 2 and square the mod separately, what this is x plus 6 is just acting as the a, and y is just acting as the b, so this is just x plus 6 all squared plus y squared, and we get rid of the i's. Same thing happening over here. We can expand all this out, I'm not going to bother with this too much, divide by 3, and we get what they wanted us to get. Sketch the curve. This is a circle. If you complete the square, you get this, and then you can move the other things over, you get that. R squared is 64, so r is 8, so it's got centers 10, 0, which is over here. Radius is 8, means it doesn't reach the origin over here. You get something that looks a bit like this, and that'll be our drawing. Next part is a z star. And now I haven't actually seen a question like this before very much in papers, so this was a bit of a curveball. A and z are both complex numbers, of course implied by the conjugation little thing here. So if you just find a to be maybe this and z to be this, as we did before, then z star is just with a minus here and a star is with a minus there. So that's fine, and then we can plug those things in, and what you're hoping happens, which is a load of stuff cancels out, and you just end up with this. We can write this, they're telling me this is the equation of a line, so let's just rearrange it to be that. So let's rearrange to get y equals, which will be this. So that's kind of cool. Let's go back to our picture, because it's telling us this line is tangent to the curve. Now this line doesn't have any y-intercept, or of course it does, sorry, but the y-intercept is 0. So, okay, where can we draw a line, y-intercept 0, tangent to this? Well, either there or there, right? There's 2 options here, which is good because it says that. Now, we need to look at this picture then, because I think we've got enough information to work out the gradient of these lines, because the radius of the circle is 8, remember. And now this is a right angle because radius is meet tangents at 90, which means if this is 10, which it is because that point is at 10, 6 squared plus 8 squared is 10 squared. It's just a scaled up version of a 3, 4, 5 triangle. So this is 6 here. So that's how I calculated this was 6. And now I'm going to do something a little bit fancy here, just because I couldn't think of how else to do this. But if you call this angle maybe alpha, this is a right angled triangle in here. So tan of alpha is 8 over 6, opposite over adjacent. So tan of alpha is 8 over 6, of course 4/3. Apologies for that email notification. Should have turned my sound off. Tan of alpha is 4/3 from there. But a little known fact is that tan of this angle here is equal to the gradient of the line that you're looking at. Because of course you could redefine a right angled triangle here, and okay, we know tan of alpha is 4/3, so this length must be 4 to 3 parts here in some ratio, 4 to 3. Which of course means the gradient, rise over run, is 4 over 3. So the gradient of this line is 4/3. The gradient of this line by symmetry is going to be minus 4/3. But of course, looking at this equation that we already have now, that means minus u over v is 4/3. Right? But now going, what else do we know here? Well, we're told the argument of a is theta. Well, the argument of a complex number is tan inverse of this over this. So v over u is tan theta. So theta is tan inverse of v over u. But of course, if I just flip this over, I get this. But of course, v over u is tan theta, as I said, so tan theta is plus or minus 3/4. There's probably better ways of doing that, but I couldn't think of any, and I think what I did there is I did some nice maths with some nice stuff here, so I thought it was worth going over, and I couldn't be able to sit here and think of a better way of doing it. So yeah, we're into the last couple of questions. I didn't really like this question for a reason I'll explain, but maybe the people in the comments will tell me why I'm wrong. First, we start with a reduction formula, which is fine. So you always want to start with some integral by parts, so either times it by 1 or break up the thing you're looking at if there's not already 2 functions here. I broke it up a little bit I used a -1 here just because I saw this -1 and thought that might be usable. Integral by parts now, so let's integrate this one a couple of times, leave this one alone, minus the integral of this one differentiated. I know lots of people do this differently with like v dv and u du and stuff like that. I just integrate this one a couple of times, leave this one alone, integrate it over there, and then have a minus integral sign in the middle. And yeah, we can put our limits in as well. Of course, sine integrates to minus cos, I should say, and this differentiates to n-1 in the front to an n-2, and then the derivative of sine is cos. This cos makes cos squared, these minuses cancel, the n-1 can go at the front, you get all this. Now this is interesting, cos of pi over 2 is 0, so the first term is 0. Sine of 0 is 0, so the second term is 0, so that all goes away, which is very kind of it. Now here, what do we do with this? Well, this is worse than this to integrate, except of course cos squared is 1 minus sine squared. So I can write that as that, then I can expand this out. And now I can break this integral into 2 bits, which is always a part of these questions. That's why I knew to do this kind of step, because I knew I'm going to get 2 things, I'm going to expand it out, then I'm going to break the integral up into 2 parts. And that's basically how this goes every time. This is of course just defined to be in-1, and this, in-2, and this is defined to be in, and then we can rearrange that, and we'll get what they were looking for us to get, which is good. Now part B is the bit that I didn't like so much. We're told this paper is 0.7 high and pi wide, so that's fine. Given the curve is this equation, so we can see immediately where this is going to come in, right? Because you've got sine to some big powers here. And we want to just find this entire area here. So we're clearly going to be integrating between pi and 0. Except if we integrate between pi and 0, this function here, we can't really use this result because this result holds between 0 and pi over 2. So how do we make this into 0 to pi over 2? Well, we can kind of see from the picture that this definitely looks symmetrical around pi over 2, right? These peaks look slightly different to each other, but symmetrical from here to here. So I'm pretty sure I can get this to work. You can also think it through much more logically. Sine of 4x, well that's sine of x, but sorry for the email notifications. Why have I turned these on? Sine of 4x is sine of x, but squashed factor 4, right? So if sine obviously does its usual rotation every 2 pi, sine of 4x does its rotation every pi over 2. And so therefore, both of these functions are symmetrical around pi over 2 because they're squashed factor 4. The squares will just make all the graph above the axis, which is fine. That's what we're looking at here. And so yeah, I think I can just halve this to pi over 2 and then double the result. That's my logic there. Now the next thing, we also have to get some more logic out because this still isn't in this form because of the 4 that's here but not here. So that's still annoying to deal with, and it's not immediately obvious that you can just apply this rule to this with a 4 here, though the mark scheme thinks that it apparently is and hasn't done any working. But what I decided to do was go back to here, and for me it was quite easy because I'm in PowerPoint. I can just edit this I can copy the slide and just put a bunch of 4s everywhere. Make sure I carry the 4s down if I'm differentiating or stuff like that, and see whether the rule will still hold. Now it does, because this thing is really nice. Cos of 4 times pi over 2 is cos of 2 pi, which is 1, but 4 times pi over 2 is 2 pi, like I said, so this sine goes away, sine of 2 pi is 0, but then likewise sine of 0 is still 0, so both those terms go away, which is good. All that's happening here is you have a 4 down here and a quarter down here, so that cancels, and so actually, once you do exactly the same thing as I did before, expand out and separate and so on, it actually just, you get the exact same result, and so the result holds. Now, the mark scheme thought that was trivial enough to not even mention and just immediately started banging in this formula. I thought it was worth showing that that this formula does indeed hold if you put a 4 here. But anyway, you divide by n here to get this, and then we can start shoving these values in. So sine squared of 4x can be written, of course this is integral of in where n is 2. So we can just put 2's into here with an I0 there. And this is with a 10 there, so we can put 10's in here with an 8 there. So that's cool. And then I0, let's very quickly work out what I0 is. Well, sine to the power 0 is 1. So this is the integral of 1, which is x. Then you put in pi over 2 to get pi over 2 minus 0, which is just pi over 2. So that's good. So that's pi over 2 there. And then here, I8 is just 8 minus 1 over 7, I6. So we'll replace that there. And then I6 is 6 minus 1 over 6, I4. So we'll put that in there. And then I4 is, and so on. And what will happen is you'll get a bunch of odd numbers up here, and the even numbers down there, and it end up going down to I0 like this. I0 we already said was pi over 2, I believe. This was another half is why that's pi over 4. But that's pi over 2, and then it's just a very simple case of dealing with all the numbers until you get to the exact right answer that they had. So we did get there in the end, and we only have one question left, which is question number 8. This question, it was a throwback for me because when I was training to be a teacher, we talked about this exact idea, and I remember showing the rest of the trainees why part A was part A. I did exactly this on the board because no one else apparently could work it out. But we have this game where you're going up steps and you can either go up by 1 step or 2 steps. So imagine 2 staircases here. Your first, if you're standing at the bottom, you can either go up 1 step or you can go up 2 steps. Those are your only 2 choices. Now, if you do the first, you have, imagine the staircase goes on much longer than 4 steps. I just obviously don't have space to write it in, but these are n step staircases. Now, if you go up 1 step, you've got remaining n minus 1 steps. And so the number of ways you can go up that staircase with n minus 1 steps is un minus 1 via this definition. And likewise here, you've got a staircase with n minus 2 steps left, so that's un minus 2. But because these are the only 2 things you can do at the start, that means that the number of ways to get up the original n step staircase was just this plus this, and so we end up with our Fibonacci sequence. Of course, these initial conditions exist because if you have a 1-step staircase, there's only 1 way to go up that, and if you have a 2-step staircase, there's 2 ways. There's either you go up like this, or you jump up both steps, so we get both those conditions there. Find the number of ways you can do 8 steps, or you just do the Fibonacci sequence until you get 8. It's actually not really the Fibonacci sequence because you only have 1, 1 to start with, though actually you could say U0 was 1 as well, because there's only 1 way to get up a 0-step staircase. But anyway, U8 is 32, and we'll have our 32. And then we have this to sort out. So we start here, and we say the auxiliary equation is going to be r squared minus r minus r minus 1 equals 0. We solve this. You might recognize this as giving you the golden ratio. So these are both distinct real solutions. So un is going to be a into this to the power n plus b into this to the power n. In FP2 exams, they seem to give you distinct real solutions most of the time. Not to say you shouldn't learn the other ones, but they seem to give you that most of the time. Anyway, from here, we put in the initial conditions. When we have 1, we just have 1 here and 1 there. Let's expand this out. I doubled everything as well, and then expand it out, and then we can put in 2. Bit more effort required here. 2 squares to 4, so then just times everything by 4 to get here. Expand this out properly. 1 times 1 plus root 5 times 1 plus 1 times root 5, and so on. We get this, we can simplify it up to be that. And so we have this equation and this equation to work with. I think I times this one by 2, and then did this minus this to get this, which divides by 4 to make this. And then I think I times that by 6, yes I did, and then did this minus this to get this, divide by 4 to get this, and of course divide by root 5 to get this, and now this and this work quite well together, because we can do this one plus this one to get 1 plus 1 over root 5 equals 2a, which divides by 2 to make this. And then, of course, we can do this minus this to get 2b's, and we get the same kind of answer. I'm just thinking you could have factorized a 1 plus root 5 here, and a 1 minus root 5 here, and then just type this into a calculator, I guess, to find a and b. But in any case, nice to do it properly. So we get a and b as that. We can put those into there. Now, when we're trying to put in 400, we put into 400 here and we get 400s there. So the fact that there's a 401 here means there's some tidying up for me to do to make this work. So okay, let's put these 2 fractions together by timesing this by root 5 or root 5 and putting them together. And likewise over here. And now this seems good, right? There's a 1 over root 5 outside. So let's factorize that 1 over root 5 by putting this root 5 outside, and likewise this one. And now, well, this is perfect then, because this just multiplies this to make an n plus 1. This is not so good, but of course these are just the wrong way around. So if I put a minus there, which matches perfectly there, I can get a 1 minus root 5, then I can put it together to get the n plus 1, and I think I have the answer as required. That was the whole paper, so thank you so much for watching, and I will see you next time.